Well, I'm happy to invite Professor Fyodor Yurievich Popelensky from the Moscow State University, and he is going to tell us about quaternionic conjugation spaces. So let's welcome.
Thank you very much for inviting me to participate in the seminar. My talk will be divided in, I would say, in 4 parts. One of them is introductory, and it will provide us with a collection of examples of what we want to discuss. Second part is maybe more or less uncomfortable for people because it's devoted to some technical questions about equivariant cohomology. But after that, we proceed to third part, which is devoted to so-called complex conjugation spaces. It contains results of complex conjugation spaces, and these results are already published by some other peoples. And the last part is dedicated to the topic of my talk, Quaternionic framing, and the results here are obtained by my students Kryazhev, Arseny Kryazhev, Dmitry Kuznetsov, and me. Well, so let us pass to the introduction part. We know, first of all, let us fix the coefficients of cohomology. It will be Z2. By this notation, we should drop these coefficients. So what we know about cohomology of complex projective space and its real locus, real projective space. We know that these rings are isomorphic, and the isomorphism has the degree, but this isomorphism is not induced by any continuous map. What we have here that cohomology of complex projective space is a polynomial ring on generator A with relation a to the power n plus 1 is 0, and degree of A is 2, and cohomology of real projective space looks pretty the same, but the generator has degree 1. There are other examples of such a feature. It's complex Grassmannians, flag manifolds, and there are some other spaces we will I will tell you some about spaces a bit later. So formally speaking, what we have a space equipped with an involution tau, such that tau squared is identity, and we have fixed points of space x tau. It consists of all points of the space x which are fixed by involution. And in these examples, on this slide, we have the following: that odd dimensional cohomology of the space x are trivial, and the rings even part of the cohomology ring of the space x itself, and cohomology ring of fixed points are isomorphic. Well, and in all examples on this slide, so in complex Grassmannians, flags, the involution is just complex conjugation. So these examples are very well known to everybody who studies topology. Okay, let's go further. Actually, this topic started not in last years, because there are many results in classical, I would say, algebraic geometry from earlier times. For example, we have theorem by Borel and Häfliger, published in 1961. So assume we have a non-singular complex projective variety defined over reals. So it is given by polynomials with real coefficients, and such that its real locus x tau. So these are points of x which are fixed by complex conjugation. So we assume that this space is non-empty. Also, we assume that homology groups of complex variety and its real locus are generated by algebraic real cycles. So we have cycles defined by real by equations with real coefficients, and then we can.
So what is T? Is it conjugation or?
Yes, tau is just complex conjugation.
Okay.
Consider a cycle on X and real locus of that cycle, X z tau. So it gives us the restriction map. So we map from the cycle to its real locus. Then this homomorphism is dividing degree by 2, and it is isomorphism between homology of X itself and real locus of X. This isomorphism divides degree by 2, and moreover, this isomorphism agrees with intersection product. So if you have a product, the intersection of two cycles, and then you pass through the real locus, it is the same as pass to real locus and then pass to intersection. So it's very old theorem.
Sorry, is it possible for z tau to be empty?
No.
How do I see this? Sorry.
Oh well, it's a very nice question, but you should. So I have no time to discuss it, but it's okay. It can be found in the paper by Borel and Häfliger.
Thank you.
It's rather long, but the question you raised is not proved in several lines.
Okay, thank you.
Not very difficult. Okay. There are other examples of spaces equipped with involution than the cohomology of the space itself and fixed point of involution look pretty similar, isomorphic, but I want to stress that this isomorphism is not given by any map by any continuous map. So let us have a look again at that stuff. So we have cohomology of the space itself, and we have cohomology of the fixed point space, and we have isomorphism. I will denote it by kappa. And this is not an isomorphism given by a map, a continuous map. So what are other examples? Maybe most famous one, besides complex manifolds, are smooth toric manifolds introduced by Davis and Januszkiewicz and investigated by Buchstaber, Panov and their students and some other people. Another interesting example is so-called polygon space. It's in some sense it's a modular space of polygons with edges of fixed length. So let us consider a polygon with length of edges described by finite sequence L. So L0, L1, L2, etc., Ln-1. And I want to consider a polygon in Euclidean space RD with edges having length described by this finite sequence. What is it? So to describe a polygon, I need to fix directions of edges. So I fix first vector. I assume that this first vector is the standard basis of RD. Other directions, also here is misprinted, and -1. So other vectors can be more or less arbitrary, but we assume that these vectors have length 1, so they belong to the sphere of dimension d-1, and which we should choose n-1 such vectors, and we must have the condition, impose this condition that this so this one is L1 V1, L2 V2, L3 V3, and finally the last one is closing this sequence. It's L0 E1. Yes, we have some action of special orthogonal group of dimension d-1, which rotates this construction around the axis, first coordinate axis. Well, and what we do, we factor out, we take quotient of this space by the action of SOD-1, and so this object is so-called polygon space.
And are the lengths allowed to be negative or 0?
No, all edges, all lengths should be positive. Thank you. Yes. Thank you. Well, so this is a polygon space. It appeared that if you consider polygons in Euclidean space of dimension 3, then you can consider an involution which changes the sign of the third coordinate, this one. Also, this one. Then this involution is inducing involution on the polygon, on a space of polygons. Roughly speaking, it's the same as passing from the spatial polygon to its mirror image. And it's more or less clear that if you consider fixed points of this involution, then you have just flat polygons. So the polygons which coincides with its mirror image. The theorem is, it was proved by Hausmann and some in joint paper of Hausmann and some other persons, that this space is so-called conjugation space. It's the first time when we meet this yes. So we have new notion, conjugation space. I will discuss it a bit later, but for this time we understand that. Well, I'm very sorry. Wait a moment, please.
It would be nice for us to see whether, okay.
Okay, I apologize for the delay. So we have cohomology of the space of space polygons and space of flat polygons, and these two are isomorphic with kappa dividing dimension by 2. It was proved by calculation, which is not so easy. So I made the reference to Hausmann papers. And there are other examples coming from symplectic topology. It's very interesting situation because these examples are not quite obvious. So we have some kind of symplectic manifolds equipped with action of torus and some other stuff, and even you can include their so-called symplectic reduction. So it's very interesting results intersecting this algebraic topology with symplectic topology, but unfortunately we have no time to discuss it. And in my opinion, the interesting part of this theory was appeared only because specialist in symplectic topology, Tara Holm, was working in this direction with those two guys. So her contribution was crucial here because she found, I guess she found some interesting examples, not just complex projective spaces, Grassmannians and some other stuff, but examples from symplectic topology. Okay, so we have some examples, more or less trivial and not trivial ones. So I think it's time to go to some definition.
Sorry, you mentioned symplectic reduction. Is the torus action just coming from, where should I see some torus action?
So it should be defined before. So it's you should have symplectic manifold with action of torus.
Oh, okay. You're talking about the, okay. So maybe I was asking about for the polygon spaces example, but you're saying for the smooth torus manifolds.
Yes.
Okay.
These two things intersect. Okay. So the last part of the talk will be devoted to Quaternionic situation. So let us start to discuss what happens there. First of all, I want to introduce 3 involutions on Quaternionic space. To be clear, we should recognize that then we discuss complex conjugation. We have two action of the group Z2 of consisting of 2 elements, cyclic group of 2 elements. It contains identity and involution tau. In Quaternionic case, we will be using another group. It will contain unit, identity element, and 3 involutions. Actually, there are generators, 2 commuting involutions, tau 1 and tau 2, and their product is involution tau 3. So this group is Z2 times Z2. Okay, so in Quaternionic case, we can consider 3 involutions given by this formula. You can see it here, but actually it's complex conjugation on Quaternionic space, because you can imagine that quaternions direct sum of 2 copies of complex numbers, but this splitting can be given in 3 different ways. So you can divide it, say, this way. Here you divide it in this way. And the third splitting is given in this way. Well, what is good about these 3 involutions? They are algebra homomorphisms. So if you take a conjugation of, you apply involution to the product of 2 quaternions, then these involutions preserve the order of the multiplication. Standard involution is not so good in this way, because if you apply standard quaternionic involution, which change signs at all imaginary elements, then this involution inverses the order. So if you take product of two quaternions, Q1 and Q2, apply conjugation, then you can take product of two quaternions, but you should change the order. Q times Q1, Q2 times Q1. Okay, so we want to change the group acting on our spaces from Z2 to the Z2 times Z2. Then we can consider examples. Quaternion space, Grassmannian, projective space, Grassmannians, flags, and so on. Since the involution doesn't change the order of terms in the product, then the involution can be defined for these spaces. Okay, here, here, and here. In this case, we see the following: the fixed point space for the action of the group Q on the quaternions are real locus. And then we have this isomorphism, which decreases dimension by 4. Looks pretty similar to complex space, to complex case. Okay, so let us go to technical details. So we need to define what is algebraic structure and cohomology, which controls such isomorphisms. So this is at this moment we need to remember what is Borel construction and equivariant cohomology. And after that, we will pass to a definition of what is conjugation space and what algebraic structure controls those isomorphisms we discussed in the first part. Okay, so consider a finite discrete group. We are interested only in two cases: in case of cyclic group of 2 elements and product of two cyclic group of 2 elements. Let us introduce universal G space. It is contractible space with a free action of group G. In our cases, they are very simple. So a universal space for cyclic group, it is infinite dimensional sphere. And universal space for the action of the group Q, there are 2 different versions. They are homotopy. They are the same from the point of homotopy theory, but if you want a concrete realization, then you have choice. For example, you can take infinite dimensional sphere in Quaternionic space, or you can just take product of 2 infinite dimensional spheres. The classifying space for the group G is a quotient of universal space by the action of G. And in our cases, a classifying space of cyclic group is infinite dimensional real projective space. And the classifying space for the group Q is a product of 2 copies of real projective space. Okay, so let's go further. So definition. So we want to incorporate equivariant stuff into the study cohomology, and this can be done in several ways, but most simple is a Borel construction for the space X. It is a so-called homotopic quotient. Since the action has fixed points, it's not a good idea to pass from X to its quotient by the action. And it's much better to pass to so-called homotopic quotient. So you take a product of universal space by X. This is 1. It's homotopy equivalent to X, and it has a free action of the group G. So the space which is obtained in this way, so you take product of universal space by the space X, and then you identify 2 points, and you identify in this product points of such type. So A point from universal space, Gx, it's action of G on a point of the space X, is identified with a point AG, comma X. Well, this quotient is Borel construction, and equivariant cohomology of X are defined to be cohomology of its Borel construction. And we will introduce this notation. Cohomology Gx, it's cohomology of Borel construction of the space X. We have the following more or less simple properties of the Borel construction.
Sorry,
Okay.
if I could just ask, how is the infinite dimensional sphere in, well, for the Quaternionic version, how is that defined?
How is defined? It's in the following way. So you consider H1, H2, H3, etc. This inclusion, standard inclusion on first coordinate axis.
I see.
Okay, so so here you have S1, S3, S, well, how many S? Oh, sorry. Well, it's oh, well, I was thinking about complex numbers, S3, S7, S11, etc. So,
Yep. Okay.
so this is direct limit.
Okay. Yeah. Thank you.
You're welcome. Okay. The properties of the Borel construction. First of all, the projection from the product of universal space E.g. by X onto Borel construction is a covering. It is. It has the same number of sheets in this covering as the order of the group G. The preimage of a point AX in the Borel construction contains exactly the same number of points as the number of elements in the group G. Assuming the action of group G on X is trivial, then the Borel construction is just direct product of space X itself with the classifying space of the group G. It's a very important thing for us because then we discuss our cases. In our cases, then we will consider fixed points, and we will be using equivariant cohomology. Then in the case of cyclic group of two elements, we obtain polynomials in one variable, and the coefficients of these polynomials are cohomology classes on the fixed points. And in the case then we consider equivariant cohomology in quaternionic case. So we pass to sorry, I just reading the comment on Jivu. Yes, thank you very much. I know this paper. Just they have two papers considering this this topic, and I have both of them.
Oh, great.
Yes.
I just received a few days ago in the email report. So I mentioned this because this is a long story. 10 years ago, actually they contacted with me to talk about it. There are some relations with homotopy group computing, some homotopy group.
Yes, I see.
They tell me, okay, finally they finished it. Yeah.
Oh, okay.
Yeah. Okay.
So it's quite well. I will. We will see some interesting things a bit later, maybe.
Yeah.
Which surprised me then I found them. So
also, I'm interested, curious, because actually the story, Julian approach to me is to talk about computing some special elements in homotopy group of the suspension of projective plane. It's backwards to my work earlier, and then we try to compute because this is a fluid manifold is 3 cells, so it's a touch map to the bottom 2 cells, which is double suspension of CP2, and we try to understand the elements. Finally, they found another way to prove. But there may be a lot of stories in the conjugation space which need some special, specific information on homotopy groups.
yes.
Yeah. Okay, but anyway, please continue. Yeah.
Thank you.
Sure.
So then we consider Quaternionic case. Then we have polynomial rings with 2 generators. In a general situation, then we have then the action of G on X is not trivial. Then we have no Q-net isomorphism, so we have not such rings. But we know that the equivariant cohomology is just a module over the ring, on cohomology ring of classifying space. Okay, so this is very standard. In some cases, we know that we have so-called equivariant formality. What is it? So then we consider fibration of such type. So Borel construction is fibered over classifying space. Sometimes we have the following. Actually, we have the fiber of this fibration is just X itself. Just X itself, and sometimes this inclusion induces surjection in cohomology. It was quite strange for me to write homomorphism in cohomology without any star, but it was more or less classical in this situation. It's in paper of Hausmann, Holm, Puppe. They used homomorphisms such row without any stars. So I continue their notation. So this map is induced by inclusion of fiber of by this inclusion. So we say that X is equivariantly formal if and only if this map is surjective. In this case, we have additive section of this map rho. The section sigma, it is homomorphism such that this composition is identity, and this sigma is not induced by any map, by any continuous map. It's just a homomorphism. So if we have equivariantly formal space and the section, then this stuff induces isomorphism of modules over a ring on the cohomology ring of classifying space. So then we have this isomorphism, but in general, it's not an isomorphism of rings. It's just an isomorphism of modules. So if you want to discuss the multiplication in the equivariant cohomology of X, it's much more difficult stuff than just this formula. One can think that equivariant formality means that if you have a class, cohomology class on the fiber, then you can expand it over the whole manifold, whole Borel construction. So if you have a cohomology class here, then you can expand it over Borel construction. So our spaces are equivariantly formal, and now we pass to the results of the third part of my talk, and we pass to the results of Hausmann, Holm, Puppe, Volker Puppe and Matthias Franz.
Sorry again. Could we just go back to the previous slide?
Okay.
The X here, I mean, G is not acting trivially on the X here in this setting, right?
Yes, here G acts non-trivially.
Okay, so before you made the statement that sigma is not realized by any continuous map, what does it mean? I mean, what does that mean given that we've got a normal cohomology and a equivariant cohomology?
Please repeat your question.
Okay, so you made the statement that sigma is not realized by any continuous map.
Yes.
And I'm just saying that I'm not really sure what this means when on the right-hand side you have an equivariant homology, and on the left-hand side.
Okay, so let us discuss it in some detail. So okay, so what? Let me denote this inclusion by letter I. It's geometrical map. So then you include the fiber into the total space of the fibration. Then you have a map in cohomology. It goes in inverse direction. So you have this one. And this is denoted by a rho. So it's pretty non-standard to denote the induced map in cohomology without any star. It's not comfortable, but okay. So it is notation introduced by Hausmann.
Okay. I think I understand now.
Okay, so
we're just thinking of the. Sorry, yeah.
Then we discuss the map sigma. Then we see the following. In the case, then we have equivariantly formal space. Then this one maps surjectively here. It's just it's surjection. Surjection of abelian groups. In this case, you can have a section. So you can construct it in algebraically. Such that if you take composition sigma, then you go back by rho, so then it is identity. And this.
So I guess the statement then is that there is no continuous map from.
Well, I'm not sure. There are no continuous map in general, which induce sigma. Yes.
Okay, from xg to x. I mean, that was my point of confusion. But yeah, okay, thanks.
So let's go to the definition of conjugation spaces. So it's algebraic stuff which is defined on equivariant cohomology and controls everything here. So let's collect the maps, the groups, and homomorphisms which are defined in some sense geometrically. So what we have here. So we have a group, cyclic group of two elements, universal space, like infinite dimensional sphere, classifying space, it's real projective space, and assume that the group C acts on the pair of space X, Y. Then we have groups. Some of them are modules, rings, and some other algebraic objects, and we have their maps. Let's have a look at that. So first of all, we have a cohomology of the pair itself here, and cohomology of fixed point space. We don't discuss here any map between them. So because we have just groups and maps which are defined from topology. Okay. On the left, in the left column, we have equivariant cohomology. So this is cohomology of the Borel construction. Then we have inclusion of fixed points here. So let's have a look. The fixed points are included in the pair of x, y. So we have an inclusion of fixed points and inclusion of corresponding Borel construction. So we have a map in cohomology in reverse direction. So in some sense, it's restriction of classes from space to the subspace. Again, a map R is defined geometrically. It is induced by inclusion of fixed points, but again, it is denoted by a letter without any stars. So it is non-standard, but okay, it was the notation by Hausmann, Holm, and Puppe, and I keep it. And since the group C doesn't act on the fixed points, then we have isomorphism here, so we can split space and classifying space of the group G. Okay, so this is what we have from the point of view of geometry or topology. And now I want to add to this diagram some new homomorphisms, which gives us conjugation structure. So we add two things. We already saw them. First of all, it is kappa is isomorphism between cohomology of x, y itself and fixed points. And this isomorphism halves the dimension, it halves the degree. Also, we add here a section of rho. So we assume that our pair X is equivariantly formal. And the last thing is most important thing here is a conjugation equation which controls everything here. So let's have a look at the previous diagram. If we take a class here, then we can apply section to this element. So we obtain class here. Then we restrict it onto the space of fixed points. So we have a class here. It belongs to this group. And since this group is a polynomials in the variable u, then we can expand this polynomial in this variable. So assuming that A belongs to the group of dimension 2m, then we have the following. R of sigma of A is a polynomial in the variable u, which has degree 2m. So it can be looking like something like this. But the third point in our definition restricts the form of this polynomial, namely the conjugation equation demands that this polynomial starts with a summand which has degree m in the variable u. So it's just only half part of general polynomial. So this polynomial should start exactly with a degree m. And other summands in this expansion should have degree less than m. So it looks like follows. No element of degree u to the power 2m, no element of degree 2 power to u to the power 2m minus 1, etc. But the first summand, which is not trivial, is exactly this one, and some other elements which are not discussed in this definition. So this is non-trivial part. So we ask that the leading coefficient should be kappa of A and some other summands. So if we have these 3 points, then we have a so-called conjugation space. And this structure H and kappa and sigma satisfying this conjugation equation is called H framing or cohomology framing of the pair XY. So in all the examples we have discussed before, complex examples with complex conjugation, toric varieties, polygon spaces. So in all these cases, we have such a structure. Well, and now I want to discuss some properties of this structure. Okay, so what we have. So this is a picture where two arrows are added, this one, and also we have explicit form of the conjugation equation. Okay, so simplest examples. Let's have a look at the simplest example. So if we have a pair which consists of an even dimensional disk and a linear involution which fixes disk of the dimension n. In this case, conjugation equation is very simple. Everybody can make this calculation. There are no choice. There are no choice for sigma, no choice for kappa. So, sorry, we have the choice, but the choice is unique. The conjugation equation is as follows. So if you have a class in dimension 2n in cohomology of the pair disk and its boundary, then after you pass to the equivariant cohomology and restrict to fixed points, then you obtain class B multiplied by u to the power of n. The same story is for n of the sphere of dimension 2n with the same involution. So you can think about it as a one-point compactification of the disk D 2n. But in this example, you need to pay attention to the choice of the section, because in this case, equivariant cohomology can give you summoned epsilon and u to the power 2n, and this is forbidden by the conjugation equation. So taking correct choice of the section, you will obtain conjugation equation. So the problem is to find correct section. Most important example is the complex projective space with the complex involution. And the conjugation equation in this case is given by this formula. So if you take class A in second cohomology of CPN, take its section.
By the way,
yes.
Really sorry. I just want to check. So the linear involution, is it something like exchange the first n coordinates with the last
exactly,
n?
exactly.
Okay.
So tau of yes. So element sigma of A belongs to the equivariant cohomology of CPN, and then you restrict it to a real locus. You obtain a class here, and it is exactly I will write it in this way. Inclusion onto elements of that degree 2. So this element expands in the polynomials in the variable u in this form. It's more or less simple exercise in calculating Euler class of Hopf bundle. But if you take any other element in cohomology of complex projective space, it's some power of the generator, then in general conjugation equation looks as it is written as it's written here. Okay. The properties of the conjugation spaces, which were proved by Hausmann, Holm, and Puppe, are as follows. First of all, they proved that sigma and kappa are multiplicative. So in the definition, they were supposed to be additive, but it's not difficult to prove that they are multiplicative, but one needs conjugation equation to prove it. What is more interesting, that algebraic structure, H-framing, it's just algebraic structure. No continuous map is here. Is that it's natural. So if you have two conjugations pairs, x1, y1, x2, y2, and you have C equivariant map between them, then the corresponding framing, H-framing. So we have H-framing for first pair kappa 1, sigma 1. And here we have kappa 2, sigma 2. These two algebraic homomorphisms commute with maps induced by F. It's very interesting. So this structure is very rigid. Moreover, from this statement, it follows that if you have a involution on the pair x, y, and if you assume that there exists at least one H-framing, then this framing is unique. Well, and finally, they proved that equivariant cohomology of the pair x, y, if you restrict class in this space to the fixed points, then you obtain inclusion and cohomology. So if actually this stuff, this statement allows us to compare two classes in equivariant cohomology, because usually it's difficult to control them, but then you restrict the class into the fixed points, then you have polynomial expansion, and then it's much easier to compare classes. Okay. So the next question is how many conjugation spaces we know, how many conjugation pairs we can found. It appears that the category of conjugation spaces is considerably rich, because it is closed under passing to direct limits, products. You can pass to Thom spaces, provided you have equivariant fibration over a conjugation space. So one can prove that equivariant connected sums for conjugation manifolds, for sure. Again gives us equivariant, gives us a conjugation pair. And most interesting theorem is as follows. Assume you have two conjugation pairs, x, y, and y, z. So in this case, the pair x, z also is a conjugation pair. The meaning of this statement is as follows. It means that you can build conjugation space from equivariant cells. So then you remember we have the first simple example that this thing is a conjugation space. And it's a very simple example, but you can glue these cells together by maps, by equivariant maps, and you obtain conjugation space. So the category of conjugation spaces is very, very big. Okay, so just to add some interesting points here, let us discuss which manifolds can be realized at the fixed points of involution on manifold. This question was, I think, it was explored in details by Conner and Floyd many years ago. But so for the result for dimension 3, I cannot even give you a reference. because I'm pretty sure that the reference I have in mind is not correct. So it was done much earlier than I could imagine. So, but so assume we have a three-dimensional manifolds, and it is then it closed orientable three-dimensional manifold can be realizable as a fixed points as a submanifold, as fixed point submanifold of a smooth involution of six-dimensional manifold. And one could take this six-dimensional manifold to be a connected sum of several copies of product of two spheres, maybe S2 by S4, maybe S3 by S3. And well, in this form, I found this theorem and the dissertation by Martin Olbermann. But I'm sure that this result is much older. But his result was as follows. Assume his result was concerned about conjugation case. In the case then this manifold, six-dimensional manifold is a conjugation space. So assume M is closed orientable and connected three-dimensional manifolds, then there exists simply connected closed spinor manifold with a smooth involution such that this six-dimensional manifolds is a conjugation space, and its fixed point is exactly our manifold M. Well, okay. So for me, most interesting part of this conjugation equation theory, conjugation spaces theory, is the explicit form of the conjugation equation. Matthias Franz and Volker Puppe proved the following statement, that coefficients of the conjugation equation cannot be arbitrary. They are defined by the action of the standard algebra in the following way. So if you take a class X in the cohomology of degree 2m in the pair xy, then the conjugation equation looks as follows. Then the coefficients can be calculated very simply. Here is it. So the first coefficient is exactly kappa of x. So the class which corresponds to x in m-dimensional cohomology of the fixed point space. And another coefficients can be calculated by applying standard squares to this element kappa of x. And moreover, standard squares in some sense commute with the isomorphism kappa, though it was artificial in some sense. It's not defined geometrically, but it should commute with the action of standard squares. So at this point, I want to finish the discussion of complex conjugation case and want to pass to Quaternionic case. Maybe you have some questions here.
Can you say a few words about the construction on the previous page again?
Sorry?
Can you go to the previous page?
Okay.
Yeah, I'm just trying to still get a better feel for how to prove something like this. Is it, I mean, the fact that you're building this from connected sums of S2 cross S4 and S3 cross S3, I'm trying to relate this to how you can, well, first of all, how is T1 acting on, how is tau acting on these two? And what are the pieces from the invariant parts that you use?
So S3 by S3, yes, well, it's a good question. I guess it could be interchanging the terms. But I'm not sure here, so it should be checked. So Martin Olbermann proved these theorems exploring some cobordism groups and making calculations in spectral sequences. So it was not
Okay.
geometrically in some sense, but
Okay.
the first statement about three-dimensional manifold can be proved more geometrically. So if you have a look at classical papers, maybe you can find references in Buchstaber-Panov papers, maybe David Svinushkevich paper. So it's very, very well known.
Okay.
For example, I can prove this theorem for dimension 2 in second to 2. So, so first of all, circle is a fixed point of on two-dimensional sphere.
Sure.
Yes, it's very easy. So, two-dimensional sphere is a fixed point of a four-dimensional sphere. Well, torus is a fixed point on product of two spheres. Yes. Then you pass to connected sums. You can prove that any connected sum of toruses is
right.
Well, and if you want to discuss unorientable manifolds, then it's also quite easy because real projective space in dimension 2 is a fixed point of a complex projective space with complex involution. And if you want to have any unorientable surface, then you just pass to this stuff.
Okay.
So in dimension 1 and 2, it's quite simple, but in dimension, so here we have proof that any surface is the fixed points of a conjugation space. Because this what is written in orange is exactly conjugation space. But this Olbermann's theorem is much more difficult. Okay, so now you pass to the quaternionic cohomology framing. Well, so what are changes here? So we ask that the cohomology of our pair of space x and y vanish for n, which is not divisible by 4. Now we consider two commuting involutions, tau 1 and tau 2, and so their composition tau 3 is again involution. So actually we have an action of the group Q, which is, let me remind it, it's product of Z2 by Z2. We fix two generators. U is dual to the involution tau 1 and V is the involution is a class dual to the involution tau 2. And if we want to generalize the conjugation structure, just writing some letters, then we must to ask for two additive homomorphisms, kappa and sigma, which I will show you on the next slide. But the question will be as follows: what is conjugation equation? It was most interesting part here, how to give correct definition of conjugation equation. Well, so let's have a look. So from the point of geometry and topology, we have groups, again models on or rings, and the maps of them which are written in the solid arrows. So kappa and sigma are artificial algebraic homomorphisms, which we add a bit later. So what we have? So we have usual ordinary cohomology of pair xy. We have equivariant cohomology of the pair xy. We have restriction to the fixed points, and the cohomology, equivariant cohomology of the fixed point is just polynomial rings in the variables u and v. And we have cohomology of a fixed point space itself. So we add two homomorphisms, which the same as in complex case. First of all, we add section sigma, and also we add isomorphism kappa. And the question is what we should write instead of conjugation equation. If we consider class R sigma of A, it is a class of dimension 4m in this ring. So it is very complicated polynomial of degree less than 4m in variables uv. But it's natural to ask that it starts, its leading term looks like this one. So you have kappa of A, and then you have some expression in variables u and v. And after that, you have a summand which has degree less than 3m in the variables u and v. So there are no summands of degree greater than 3m in the variables u and v. But the question is, what is the correct choice of the polynomial p3m of the variables u and v? What should be written here, and what should be written here? What are the summands of degree less than 3m? Okay, let's have a look at the motivation examples. Motivating examples for sure are Grassmannians, Quaternionic Grassmannians. And if we have a look at the image of, so what we do, we take an equivariant cohomology of Grassmannian, Quaternionic Grassmannian, and then consider its map to the equivariant cohomology of the real Grassmannian. Then after some inspection, one can obtain that the image of this restriction map should belong to invariant part of this polynomial ring. What invariant of what? Indeed, when one can show that there is an action of the group GL2 over Z2. It acts on the polynomials in two variables by linear substitutions in generators U and V, and the key idea is that the image of this restriction map belongs to the invariant part of this polynomial rings. From how one can find it, it's very geometrically. So we have an element I plus j in the quaternions. Conjugation by this element gives us conjugation on the cohomology of the complex quaternionic Grassmannian, but it acts on just as identity, because the element I plus j can be connected by a continuous path with the unit in quaternions. That's why I plus j acts on the ordinary cohomology of Grassmannian by identity. But if you look at the equivariant cohomology, you will easily can see that conjugation by element I plus j interchanges generators U and V, because I plus j is outer automorphism of the group Q. Conjugation by two other elements, I plus k and j plus k, interchanges one of the variables u and v with the sum u plus v. It means that these three conjugations generate the action of the group GL2 over Z2. Well, the next question is, what are the invariants of this action? And it's quite funny to know that It's very, very old paper, which is more than 100 years. It was written more than 100 years ago. It's fundamental system of invariance of general modular linear group. And in our case, the answer is very simple. It's polynomial ring on two generators. And I'm pretty sure that Jivu should be familiar with so-called Dixon invariants. And these are Dixon invariants for case N2.
Yes, yes.
Yes, yes. It was quite funny for me to find them here. Actually, if you consider action of a group, so you can discuss the same theory for action, not for action of group Q, but maybe for product of groups Z2 to the power n. So there are no quaternions in this case by famous theorems by Frobenius, maybe by Adams, but nevertheless you can give a definition of conjugation equation and so on, then you have Gay-Dixon invariance and for n variables. The statement is the same. So the invariant ring is a polynomial ring on explicitly described generators. In the case of two variables, they are written here, f2 and f3. So the correct form of the conjugation equation is written here. So leading term is just the power of the generator f3, and the other summons written here is some polynomial in elements f2 and f3. Okay, so what we can found is so this is this I described here why the coefficients of kappa of A should be f3 to the power of m, because we see that there could be many invariant polynomials in this degree, but passing to localization, we have an isomorphism, and some simple calculation in localized rings shows that coefficient should be f3 to the power of m, no, not other guys. Okay. So also we can discuss n-framing. Then we do not impose the condition that the last part is symmetric polynomials. It can be not GL2 invariant, but actually I have no examples of such framings. Well, so in general, n-framing is a Q-framing if our space or pair of space have three automorphisms, theta 1, theta 3, and theta 2 and theta 3, such that theta r commute with the involution tau I and interchanges to other involution. Means that theta 1 tau 1 is tau 1 theta 1, but theta 1 tau 2 is tau 3 theta 1, and tau 1 tau 3 is tau 2 theta 1, something like this. In this case, if such three automorphism exists, then n-framing should be Q-framing. Okay, so let us consider properties of framings. So sigma and kappa are multiplicative, they are natural, and the framing is unique provided it exists, so it extends to direct limits and products. So it's absolutely parallel to the theory of complex conjugation. Instead of extension, we have a bit weaker theorem. So we assume that X is a cell complex built from cells of dimension divisible by 4, and gluing maps are Q invariant, then one can prove that this space X is n-framed. So I cannot prove theorem of extension in full generality, but only in the case then I glue cells in the order increasing the dimension. Because in complex space, in complex case, it was not necessary. You can glue cells in any order. But here I need to build this cell complex in a standard way, increasing dimension of cells. Okay, so examples. I'm sorry for misprint. Okay, so the pair. So we take a disk of dimension K4 for K, and conjugation equation in this case is this one. There's no choice here. So if you try to calculate what it should be, that the only possibility here is. For sphere, you should be careful because you need to find the section. Correct section. Okay. For projective space, the conjugation equation is much more interesting. So let me remind you that in complex case, the conjugation equation was very simple. It contains only two summands. Here we have three summands. So it's not just exercise in calculating Euler class of Hopf bundle. So it should some extra work should be done here, at least to find this summand. Okay, so and here is the explicit form of the conjugation equation. So assume we have a Q-framed pair, then its conjugation equation can be written in the following form. So since you have all summands in this conjugation equation are monomials in the generators F2 and F3 generators of the Dixon algebra, let me remind you that F2 is this polynomial and F3 is UV U plus V. Then the statement is as follows. If you rewrite the conjugation equation in this form, collecting monomials of this form, then coefficient of this element, it should be some expression in the element A. So you take element A and want to apply its section sigma and then restrict it to fixed points and then expand in the variables U and V. So you need to expand it not in variables U and V, but in variables F2 and F3. Then the coefficients, which are written here as A capital IJ of the element A, are cohomology operations applied to the element kappa of A. Namely, so that we start from just kappa of A, and then if you take element, the coefficients A capital IJ of the element A, so then you take Milnor element SQ with indices G, I, and apply it to the element kappa of A. So this theorem gives you explicit form of the conjugation equation in quaternionic case. And I have a conjecture that the same formula can be written if you consider action of the group of such type. Well, This theorem has very, I would say it's the proof is not easy because first of all, you need to prove that the coefficients are cohomology operations. And after that, you can identify these cohomology operations by using some test space like product of quaternionic projective spaces. Well, I think it's time to finish. So our results are as follows, just to summarize. We develop some general theory of conjugation, quaternionic conjugation spaces, and found explicit form of conjugation equation. Yes, that's all. Thank you.
Okay, thank you very much. Are there any questions or comments, remarks? Jay, do you have any questions? Jay?
No question. It's a very nice talk. Yeah.
Oh, yeah, really very nice talks. Thank you very much.
Yeah, yeah.
Thank you.
Thank you. Yeah.
Oh, well.
Vasily disappeared, right?
Yes, I see. I guess his connection was lost.
Right.
Okay, maybe so if you're interested in this topic, maybe we can have some communication a bit later on that, maybe some by email and something like that.
Yeah, yeah, sure. That's nice. Yes. Yeah. It's nice to get a theory.